So the next speaker is Toru Takisaka. We're going to talk about Gacs quantum algorithmic entropy.
Thank you. So today I'd like to talk about Gacs quantum algorithmic entropy. The table of contents is as follows. Today I'd like to introduce some quantum modification of classical descriptive complexity. So first, we recall the notion of lower semi-computable semi-major, one of the notion of classical descriptive complexity, and introduce our quantum modification of lower semi-computable semi-major, and discuss some properties. And then we state our main problem and main result. From Wolf complexity is the notion of actual information content of binary strings. Namely, the Kolmogorov complexity of finite string W is the minimum length of input strings, which makes some optimal Turing machine output W. In early 2000s, several approaches to quantize this notion is proposed by these authors. Over the decade has passed since this definition proposed, but we still don't know well about them. But to make this notion more reliable and more applicable to other research areas, making relationships between them more clear would be important. In fact, there is a theorem named Levin's coding theorem in the classical domain, which shows several different formulations of descriptive complexity are equivalent. This theorem makes Kolmogorov complexity more reliable notion. So there is an analogous result in quantum domain. It would also make this notion more reliable. Belson et al. Quantized the notion of Kolmogorov complexity, while Gacs quantized the notion of universal semi-major, which are said in Levin's coding theorem that these are equivalent. So it would be natural to expect these two quantum notions also have some good relationship. There are several tasks to examine the relationship of these two notions. First, first we find that the definition by Gacs needs some correction in its fundamental facts. Second, we need to define the prefix version of the definition by Belson et al. Qubit complexity. Namely, definition by Belson et al. Is based on the notion of plain and non-prefix-free Kolmogorov complexity, which is slightly different from the one which is compared in Levin's coding theorem. So today's talk is about this. Gacs defined lower semi-computable semi-density matrices as a quantum analog of lower semi-computable semi-majors. Unfortunately though, it turns out that Gacs proof of the following two theorems has some flaw. The first theorem is about the existence of universal matrix, which is used to define the quantum complexity function H. The second theorem asserts that the function H is an extension of classical complexity in the following term. The former is apparently expected to be true, since otherwise we do not have the definition of quantum complexity H. And the latter is also expected to be true, because it is known that an analogous fact holds for the definition by Belson et al. So if the latter claim is false, then it means these two notions, these two notions are far from equivalent. In this talk, we construct an infinite-dimensional modification of Gacs lower semi-computable semi-density matrices and discuss their properties and the problem of. In particular, we show the problem of Gacs argument can be fixed if we adopt some additional assumption. The assumption seems relatively natural, but we believe it should be derived from our definition itself, and showing that is one of our main future tasks. We also show that universal operators should have certain non-trivial form, so we expect that we can find more interesting features. There is a related work with ours, which is done by Tanaki in 2006. While the eventual goal of two works are somewhat different, there are several technical overlaps between his works and ours. So we recommend interested listeners to read his work. So first we recall the notion of lower semi-computable same measure, another formulation of descriptive complexity of graphical strings. F is lower, a real valued function of binary strings is called a semi-measure if it is non-negative, and this sum is lesser than 1. F is lower semi-computable if it can be approximated by a sequence of uniformly computable functions, which is increasing and converges to F pointwise. We call that sequence, this F tilde, a lower approximation of F. One would question that why this function can be a notion of descriptive complexity. Actually, this is an abstract condition of probability distribution when we input a random binary sequence to a prefix Turing matrix. Just like for Mogorov complexity, we use some optimal same measure, that is universal same measure, to measure complexity of strings. Here we say M is universal if for any semi-computable same measure M prime, there is a positive constant C, such that for all x we have this inequality, we can show a universal same measure does exist since this function is universal. Here, this Mn is an effective enumeration of lower semi-computable same measures, and each lower semi-computable same measure is equal to some Mn, so we have this inequality. The fact that we can enumerate all lower semi-computable same measure is crucial in this proof, and problem in Gacs paper comes from the fact that we have some difficulty to enumerate lower semi-computable semi-density operator, which is the quantum analog of lower semi-computable same measure. Finally, Levin's coding theorem shows that negative logarithm of m of x is equal to prefix Kolmogorov complexity of x and k up to a constant. Before defining our quantum modification of universal same measure, we briefly review some quantum notions. What corresponds to single binary bit is qubit, a unit vector in C squared. We write its basis 0 and 1 and use that as usual. Similarly, what corresponds to n letters binary string is a unit vector in the n tensor of C squared. And the set of all binary strings corresponds to the direct sum of these spaces. We call this space H, and corresponding orthonormal basis is called a computational basis. Also, let L of H be the set of all bounded Hermitian operator on H, and this TQ be the set of all complex number with rational coefficient. So now we will introduce our modification of Gacs definition. First, rho in L of H is called a semi-density operator if rho is positive and its trace is less than 1. Second, rho in L of H is lower semi-computable if there exists a sequence of Hermitian operator rho n, which is identified by a single computable function psi. Single computable function psi by this equation. Namely, the value of psi the value of psi and wv represent the value of wv's entry of rho n. And rho n is increasing sequence and converges to rho in weak operator topology. We call upside or corresponding sequence rho lower approximation rho. If the sequence is not increasing but decreasing, then we call rho upper semiconductor. If the sequence rho satisfies this inequality instead, then we call rho is computable. So let me answer several natural questions. First, is there any relationship between computability or semi-computability of rho and this function? The answer is partly yes. Rho is computable if and only if this function is computable in a classical sense. On the other hand, we don't have any good relationship between the semi-computability of rho and this function. Next, any lower semi-computable semi-density, the next question, in classical domain, a function is computable if and only if it is lower and upper semi-computable. Does it also hold in our quantum version? The answer is yes. Rho is computable if and only if it is lower and upper semi-computable. Next. Any lower semi-computable semi-density operator can be decomposed into this form, eigenvalue decomposition in the discrete form. Do this function m and the set psi have any good property in a sense of computability? For example, m is always lower semi-computable and so on. We do not have necessary conditions so far, but have some sufficient condition. We say a sequence of states is uniformly computable if any component of any vector this can be approximated by a semi-recursive function psi tilde. Then for any uniformly computable sequence of states and lower semi-computable semi-measure, this operator always becomes lower semi-computable semi-density operator. There is also a property which does not hold in our quantum version. For any lower semi-computable semi-measure m, we can take a positive approximation function of m. In fact, if this psi is a lower approximation of semi-measure m, then so is this function phi. This is not true in our quantum version. There is a lower semi-computable semi-density operator which cannot be approximated by any sequence of positive operators. The counterexample is as follows. Each entry of this infinite matrix is uniformly computable. So rho is computable, and hence it is lower semi-computable. On the other hand, any operator sigma which satisfies this inequality is equal to C times rho for some appropriate constant. But for any non-zero real number C, we cannot make C times rho rational valued operator, so we can't approximate this operator by a sequence of positive operators from here. So, now we would like to see our main problem. Just like the classical case, we define the universality of lower semi-computable semi-density operator as follows. If we could enumerate all lower semi-computable semi-density operators, we were able to construct a universal element in completely analogous manner as the classical case. Formally, an effective enumeration of all lower semi-computable semi-density operator is a computable function with the following property. First, for any n, psi tilde bar n is a lower approximation of some lower semi-computable semi-density operator. And conversely, for any given lower semi-computable semi-density operator rho, we can find some natural number n, which makes the psi tilde bar n the lower approximation of that operator rho. Gacs claims it is possible to show the existence of this enumeration just analogous to the classical case, but this is not true. To see its difficulty, let us review how to enumerate all lower semi-computable semi-measure, classical. Let this sequence be an effective enumeration of all partial recursive functions and consider the following algorithm. For an input n, let alpha w equal 0 for every w, and dovetail all the computation on phi n for an input wk. Whenever phi n holds for some input, check whether these two conditions hold, and if so, then let alpha w is equal to phi n wk. Otherwise, do nothing and go back to dovetail computation. In short, this is an infinite update process of a function on binary strings, which starts from zero function. Let psi tilde of wtn be the value of alpha w after the t-step computation of the algorithm above for an input n. Then this psi tilde is an effective enumeration of all lower semi-computable semi-measure because it satisfies the required two conditions. We could naively interpret this proof into the quantum setting as follows. It seems a little bit complicated, but it is aimed to work as follows. Starting from an infinite matrix with all entry 0, we update its entry pointwisely according to the output of phi n. We do this update process, keeping to satisfy the monotonicity and semi-completeness condition. But this modification does not satisfy the second condition, namely, we cannot generally find an n which makes psi tilde a lower approximation of given lower semi-computable semi-density operator. First, psi does not approximate the same semi-density operator as which is approximated by phi n. For example, let's consider the following easy function. This function outputs no matter what the value of k is, outputs 1 second if both of w and v are lambda or 0, and otherwise output 0. We also require this phi n holds first for this input, and second for this input, and third for this input, and so on. Then this function phi n 0 is a lower approximation of this operator. On the other hand, updating process of the algorithm above for input n0 is like this. Starting from 0, first this entry is updated, and then this entry is updated. But this operator never be updated to this operator. This monotonicity breaks in these two operators. So phi n0 and corresponding psi bar n0 approximate different operator. algorithm simply cannot produce a raw approximation of certain operator. In fact, any raw approximation of this operator is not positive sequence as we have seen before. But any approximation sequence made from the algorithm starts from 0, so it can't approximate this operator. To avoid these problems, we try to construct somewhat weak enumeration like this. Namely, for given lower semi-computable semi-density operator O, we can only find an n such that this function enumerates this function approximates an operator which multiplicatively dominates rho, not rho itself. This enumeration is enough for our purpose, since we can do the same argument as the case we have the strong enumeration. Also, we adopt some additional assumption to show the universality. Roughly speaking, for given lower semi-computable operator rho, we assume there is a sequence rho n with the following property. First, each rho n has a finite matrix representation with respect to the computational basis. This property enables us to import each rho n to some natural number, so we can avoid the first problem we explained before. Second, rho n is positive but almost increasing sequence. That is, we allow certain error about the monotonicity of this sequence. This enables us to avoid the second problem. Here we restate our assumption more precisely. This condition 1 is a condition of almost increasing. And this condition 3 is a condition of finite matrix representation. Under these conditions, we can show the existence of universal operator. So we briefly see the proof. First, we construct the algorithm of a weak enumeration of lower semi-computable semi-density operators. Actually, it is almost the same as the first algorithm we constructed. But there is one difference. That is, we regard each phi n and function from n to the set of all finite dimensional Hermitian matrices with each coefficient in CQ. Making this change, we can say that if psi n itself is a lower approximation of some lower semi-computable semi-density operator, then the corresponding sequence produced by the algorithm, this sequence, also approximates the same operator. So if we want to know which natural number makes psi tilde a lower approximation given lower semi-computable operator, we can just choose the index of its lower approximation function. Notice that the condition does not hold in the first algorithm because the monotonicity of sequence of operators is easily destroyed when we update the value of entries 0.5. Also, for any lower semi-computable semi-density operator rho, we can find a lower approximation of this operator, which starts from 0. So the approximation sequence is positive sequence. Here, sigma is something like error, and this operator multiplicatively dominates rho. Using these two facts, we can show that the psi tilde is a weak enumeration of lower semi-computable semi-density operator. So we can show this operator nu. This operator nu is universal in the same manner as the classical case. Once we show the existence of universal operator, we can define the quantum algorithmic entropy of qubit strings as follows. Here is a refined version of Gacs' second claim, which we state in the first section. Assume a universal operator exists. Then for any uniformly computable orthonormal system, a quantum algorithmic entropy of psi n is equal to the prefix Kolmogorov complexity of index n after the constant. In particular, the computational basis is obviously uniformly computable. So this equation holds. We can understand this proposition claims that our quantum algorithmic entropy is an extension of classical Kolmogorov complexity. This proof is rather easy, so we omit the proof. We have some corollary which is used in the proof of our second result. For any uniformly computable orthonormal system, this function is a universal same measure. Finally, we see yet another result which shows a universal operator should have some non-trivial form. In this talk, we would like to work on more particular example. Namely, we showed that a universal operator is not diagonal. That is, this operator is not universal. Here, the function m is a universal semi-measure. It is rather disappointing if mu is diagonal. Since then, a function h becomes merely a linear combination of classical complexity. But actually it is not, so we expect a more interesting feature of mu that could be found for future. The proof is based on the previous corollary. Let psi n be a state of this form, and the meaning of the elements of the computational basis with its length n. Then for the previous corollary, this function should be universal, but it is not true. In fact, the function which outputs n bar on n multiplied with n's power of 2 is also a lower semi-computable same measure and cannot be dominated by n bar. The more general statement is true, and this is our second proof. So this is end of my presentation. Thank you for this.
Any questions? So there's a very intuitive interpretation of Kolmogorov complexity. Does this actually extend? The interpretation, classical interpretation of Kolmogorov complexity, does it actually extend these definitions?
Yes.
Yes. Any more questions? We thank the speaker again. Yes, you got 51 slides out of 50.